What if a submarine could navigate in space? Picture this. You're floating in the crushing darkness of the ocean depths, 3 miles down where the pressure could flatten a car like a soda can. When suddenly your sonar picks up something impossible. It's not a whale or a thermal vent, but the vast emptiness of space itself, stretching out before your submarine's hull. It sounds absurd, but stick with me, because the physics of making this work are far more fascinating than you might expect. Let's start with the obvious problem. Space is a vacuum, and submarines are designed to keep water out, not air in. Your typical nuclear submarine is built like a steel cigar, designed to slice through water with minimal resistance. But here's the thing that most people don't realize about spacecraft design. We're essentially already building submarines for space, the International Space Station. It's basically a submarine floating in an ocean of nothing, maintaining precious atmosphere against the infinite void, trying to suck it all away. But our hypothetical space submarine would need some serious modifications. First, forget everything you know about propulsion. Those massive propellers that push submarines through water would be about as useful in space as a screen door on a submarine. In the vacuum of space, you need reaction mass. Every action has an equal and opposite reaction, so to move forward, you need to throw something backward. Our space submarine would need thrusters, lots of them, positioned strategically around the hull. Now here's where things get interesting. Traditional spacecraft use chemical rockets or ion drives, but our submarine has something most spacecraft don't: a nuclear reactor. Modern submarines like the Virginia-class pack nuclear reactors that can run for decades without refueling. In space, this becomes an incredible advantage. While other spacecraft worry about solar panel positioning and battery degradation, our space submarine could generate consistent power for its electric thrusters indefinitely. The reactor brings up another fascinating parallel. Submarines already live in an environment where a single hull breach means death. Space is no different. The engineering challenges are remarkably similar. Maintain life support in a sealed environment. Manage thermal regulation and ensure structural integrity under pressure differentials. Instead of keeping thousands of pounds of water pressure out, you're keeping 14 pounds per square inch of air pressure in. But that's just the beginning of our engineering puzzle. Navigation in space would require a complete overhaul of the submarine's systems. Sonar, the submarine's primary sense in the murky depths, would be useless in the vacuum of space where sound can't travel. Instead, our space submarine would need to rely on radar, LiDAR, and optical sensors. Imagine the submarine's conning tower bristling with radio dishes and telescopes instead of periscopes. The real breakthrough comes when you consider what makes submarines so effective underwater. Stealth. Nuclear submarines are among the quietest machines humans have ever built, designed to slip through the ocean undetected. In space, this translates to thermal and electromagnetic stealth. A space submarine could run nearly silent, its reactor carefully shielded, its heat signature minimized through advanced cooling systems. While other spacecraft light up like Christmas trees on infrared sensors, our submarine could ghost through the solar system practically invisible. And then things get even more interesting when you think about the crew. Submarine crews are already trained for long-duration missions in confined spaces, dealing with recycled air, limited privacy, and the psychological pressure of being surrounded by a hostile environment. These are exactly the skills needed for deep space missions. The transition from 3 months under the Arctic ice to 3 years traveling to Mars isn't as dramatic as you might think. Here's something that would blow your mind. The submarine's ballast system could be adapted for space maneuvering. Instead of taking on water to dive or expelling it to surface, our space submarine could use reaction mass tanks. Want to accelerate toward Jupiter? Expel mass in the opposite direction. Need to slow down for orbital insertion around Europa? Throw more reaction mass forward. It's elegant in its simplicity. The navigation techniques would evolve too. Instead of dead reckoning through ocean currents, our space submarine would navigate by pulsars, using their precise timing as cosmic lighthouses. The same mathematical principles that help submarines plot courses through three-dimensional ocean space apply perfectly to plotting trajectories through the three-dimensional void of space. But here's where our space submarine really shines. Exploration. Think about what submarines do best. They slip into hostile environments, gather intelligence, and return home with data. Now imagine that capability applied to space exploration. While other spacecraft announce their presence with bright engine burns visible from millions of miles away, our space submarine could drift silently through asteroid fields, approach potentially hostile alien artifacts, or conduct reconnaissance of enemy spacecraft without ever being detected. The life support systems would be remarkably similar to submarines. Already scrub carbon dioxide from the air, generate oxygen from seawater, and recycle every drop of water aboard. These closed-loop life support systems are exactly what you need for long-duration space missions. The submarine crews who spend months breathing recycled air and drinking yesterday's coffee would find the transition to breathing recycled air and drinking recycled water in space to be just another day at the office. Temperature regulation presents an interesting challenge. In the ocean, submarines can dump excess heat into the surrounding water. In space, the only way to lose heat is through radiation, which is incredibly slow. Our space submarine would need massive radiator panels, probably retractable, to avoid detection, to dump the enormous amount of heat generated by its nuclear reactor and life support systems. And here's the kicker that makes this whole concept even more plausible. We're already halfway there. The nuclear submarines prowling our oceans today are technological marvels that could, with modifications, actually survive in space. The pressure differential is reversed, but the engineering principles remain the same. The life support systems exist. The nuclear power source is proven. The crew training is established. The real magic happens when you consider the mission profiles. Instead of patrolling shipping lanes or hunting enemy submarines, our space submarine could conduct multi-year exploration missions to the outer planets. It could lurk in the asteroid belt, studying objects for mining potential. It could investigate the moons of Jupiter, using its stealth capabilities to approach these worlds without contaminating them with loud rocket exhausts. Picture this: 200 years from now, in the depths of space between Jupiter and Saturn, a lone space submarine drifts silently through the cosmic void. Its nuclear reactor hums quietly, providing power for life support and station-keeping thrusters. The crew, descendants of today's submarine sailors, monitor their sensors for signs of life on distant moons while their vessel maintains perfect stealth in the darkness between worlds. And thus, we arrive at our answer. The marriage of submarine technology and space exploration isn't just possible, it's inevitable. The same engineering that keeps our submarines hidden in Earth's deepest trenches could one day keep our explorers invisible among the stars, turning the vast ocean of space into humanity's newest hunting ground. If the idea of submarines exploring space captures your imagination, you're not alone. Some of the most innovative minds in aerospace are already drawing inspiration from the depths of our oceans to reach the depths of space.